In the last class, we have seen definition of a binary operation, definition of semi-group, existence of identity, and existence of inverse. So with the above conditions, we define a new concept called group here. Formal definition. Let G be a non-empty set equipped with a binary operation circle. If the following postulates hold good in G, then bracket G circle is called a group. Here we are taking a non-empty set G and with a binary operation. If elements of G satisfy the following conditions with respect to the binary operation circle, then bracket G circle is called a group. Let us read. Property 1. A comma B belong to G implies A circle B belong to G. Here A and B operated with the binary operation and the result belongs to G. This is called closure axiom or closure property. The next one is, here we are taking three elements in the set G. Bracket A circle B circle C is equal to A circle bracket B circle C for all A, B, C belong to G. If for all the elements of G, this condition satisfied, this is called associative law or associative property or associative axiom. The next third one is, if there exists an element E belongs to G such that E circle A is equal to A and A circle E is equal to A for all A belong to G, then E is called identity element in G. Here we are searching for an element with this property. E is operated with A from left side and right side, we get the same A. This must be satisfied for all the elements of G. This E satisfies for all the elements of G with this, then E is called identity element. Next, inverse element. For each A belongs to G, there exists B belongs to G such that A circle B is equal to E is equal to B circle A, then B is called inverse of A. If there exists a B for each A, that means for each A there is B. If we take some X, we get some Y with this property. If B exists, then B is called inverse of A. If B does not exist, we cannot say. If for each A in G, there exists a B with this property, that is A circle B is equal to E and B circle A is equal to E, then B is called inverse of A and vice versa, A is called inverse of B. So if G satisfies, that means if elements of G satisfy the following axioms with the binary operation circle, then G circle is called a group. Next, another definition called abelian group or commutative group. Let G dot be a group. Here we are considering a group. If A circle B is equal to B circle A for all A belong to G. We have seen in the last class for integers it is true. Here we are generalizing the property. A circle B is equal to B circle A for all A belong to G. Then G is called an abelian group or commutative group. So here this must be verified for all the elements of G, not particular 2 elements or 3 elements or 4 elements. If this is true for all the elements of G, then G is called an abelian group. We are taking a group and elements of G satisfy this condition, then G is called abelian group. Here this abelian group by famous mathematician Abel, this property is called abelian group by a famous mathematician Abel, or in general we call it as a commutative group. Next, finite group and infinite group. Every set contains some elements. It may be finite number of elements or infinite number of elements. Here, let G circle be a group. If G contains a finite number of elements, then G is called a finite group. Here we are considering a group, and if G contains a finite number, say 10 or 20 or 100 or 500 like that, then G is called a finite group. If G contains an infinite number of elements, then G is called infinite group. Here we are taking a group, and if this group contains infinite number of elements, then G is called infinite group. Next, we go to the some definition. Order of the group. Order of the group means the number of elements in a group G is called order of the group. Suppose if a group G contains 4 elements, then we say order of G is 4. If a group G contains 6 elements, we say order of group is 6. If G contains some 27 elements, we say that order of group is 27. If G contains infinite number of elements, we say order of G is infinite. Here we go to some 2 important theorems. In a group, we have seen there is a property called identity element. How many identity elements exist in a group? In our knowledge, in general, in the set of all integers, with respect to addition, there is a 0. For any element A plus 0 gives A, and 0 plus A gives A. In general, in the set of integers, there is only one element 0. So like that, how many elements exist in a group? In any set, not a set of integers, not a set of real numbers. Here, the statement says identity element is unique. If at all identity elements exist, it is unique. That means there is only one identity element in a group. Let us go to the formal proof of the theorem. Let G dot be a group. Suppose if possible, E and F are 2 identity elements in G. Here I am taking 2 identity elements. If at all there exist, if possible, suppose. At the end, I show that E is equal to F. E and F appears but are the same. Then by definition, using the definition of identity element for E, we have A dot E is equal to E dot A is equal to A for all A belong to G. And since F is also identity element, A dot F is equal to F dot A is equal to A for all A belong to G. Since here E is identity element and F is element of G, here I am using the property that E is identity element and F is an element of G. So using identity property, we get F dot E is equal to E dot F is equal to F. Here I am using E is identity and F is element of G. So when E is operated with F, we get the same F. From left side or from right side, we get the same F. And next I use that F is identity element and E is element of G. Here I am using F is identity element, E is element of G. So here we get E dot F is equal to F dot E is equal to E. We get the same element E. Here see this, here E dot F is equal to E and here E dot F is equal to F. So I will write E dot F is equal to E and E dot F is equal to F. Here E dot F is same. So we can say E is equal to F. Therefore, E is equal to F. In the beginning, I have taken E and F are 2 identity elements, but we have shown that E is equal to F. Therefore, identity element is only one. That means identity element is unique in a group. If at all identity element exists, it is only one element. Next, we go to the theorem. In a group G, inverse of any element is unique. In the definition of group, we have seen if there exists an element B belongs to G for each A belongs to G with the property A circle B is equal to E is equal to B circle A, B is equal to inverse of A. How many inverse elements exist? A question rises. Here the theorem says only one element exists as the inverse for all the elements. So we go to formal proof. Let G dot be a group. Let A belong to G. Let E denote identity element in G. Here I am taking a group. Let A belong to, that means A is any element in the group G. And here I am using standard symbol E for the identity element. Here I will suppose there is two inverse elements for A. If possible, suppose B and C are inverse elements of A. I am supposing B and C are inverse elements of A. Then by definition of inverse element, we get A dot B is equal to B dot A is equal to E, and A dot C is equal to C dot A is equal to E. Here I use the property of the identity element. First I will take B. Using that E is identity element, we can write B is equal to B dot E. And from this E, I can write here A dot C. Here E is equal to A dot C. I am writing here in the place of E, A dot C. Here I am using associative law, changing the brackets for the elements B dot A. I will write B dot A dot C. And again from the above, we can write B dot A is equal to E. So we get E dot C. And using that E is identity element, we get E dot C is equal to C. Here I have taken B and have arrived to C. That means B is equal to C. In the beginning, we are supposing B and C are two inverse elements of A, but we have proved that B is equal to C. That means there is only one inverse element for A. Here we have taken A is any element of G. So I conclude for any element of G, if inverse element exists, that is only one element. So I will say inverse of A is unique. Hence inverse of each element of a group is unique. So in this class we have learned definition of a group, definition of commutative group, and uniqueness of identity element and uniqueness of inverse element.